How's that? Is that full screen for everybody, ICerS?
Yeah, I can see presentation.
Perfect. Okay, thank you very much for the introduction, Mazier. It's an honor to be here with everybody at the Iranian Ceramic Society. Anybody that'll listen to me talk about silicate glasses and ceramics, it's an honor to do so for them and for everybody who's joined us from all around the world. So my experience as a postdoc now has been in the area of silicate glasses and glass ceramics. I'm a geologist by training, so I come at this from usually perhaps a different from a different perspective, as most of you who might be coming from the engineering and more applied sciences side of things. But I think this is actually a huge advantage because when we can when we can talk across fields, we really start to understand things a lot better. And that's certainly been my experience at CERTEV, where I work with chemists, physicists, and ceramicists together. So in developing this talk to present for you today, I think a lot about the structure of silicate glasses and crystallization processes. And one of the things that has been said since at least the 80s, if not much earlier, is that our goal with creating glasses and glass ceramics is to fill some functional purpose. And so in order to design or engineer a glass or ceramic for that purpose, we need to know how to...
Ben, sorry.
Yep.
Ben, could you just wait a minute? I need to record your video. We forgot to start recording. Just let me just start the recording from now. If you want to repeat your introduction a little bit earlier you started,
Okay.
Then I'll start recording. Just record the meeting. Now
So
we are
thanks. So as I was starting to say, when we're trying to produce a glass or glass ceramic, we have a goal in mind. And the object of any of our production of these materials is for some application, which means we need to know what properties that material has. One of the ways we can manipulate those properties is by manipulating the structure of that material. And so that's what I want to focus on today. Raman is an excellent structural probe for all sorts of crystalline materials, but also as a probe for non-crystalline materials. And we'll look at what the Raman effect is and how we apply it. So the Raman effect was first observed by this guy here, Sir C.V. Raman. He won the Nobel Prize for it, I think back in the 30s. And he discovered this effect where radiation had changed wavelength when it interacted with the material. And so we're going to see how that is applied today. For most of you, when you make a polycrystalline ceramic, or in this case, it's a photograph of a rock, a granite, there's many different phases there. And with one experiment, a Raman experiment, you can identify many different phases very rapidly. These spectra surrounding the photo are of a carbonate material, a fluoride material, and two different aluminosilicate materials. And you can see in these spectra, there's a bunch of peaks that are quite different at different frequencies, and we can use these to fingerprint the material. We can go a step further and map where the phases are in our ceramic by using some function of the intensities, and we can measure the Raman spectra very rapidly for very short times over large, hundreds of microns in about an hour, and get all of the different phases and some degree of confidence about their chemistry from a Raman experiment. Any individual measurement, the spectra I just showed you, or this raster map that you're looking at today, they can be done for a well-crystalline material in about 10 seconds. So no other technique gives you the type of information and as quickly with as little processing as Raman spectroscopy, and that's why it's exploded in its use in every field of science. It's used in forensic science. You can actually use Raman to determine the different types of tears from people if they've fallen on the couch or on a piece of fabric. They use it in identifying the types of drugs in medicine. It's used extensively in the food industry. And a lot of that is a product of the developments that have made Raman so powerful. First, you'll see in the graph in front of you, this is the number of publications using Raman by year, and there's very few, under 100 per year, until the advent of the laser, once we have, which gives us monochromatic light, and we'll talk about why that's important later on. There was an exponential rise until we found we developed the technology for CCD detectors, and the final explosion came upon the development of confocality, and we'll discuss how this is related to depth resolution in general. This graph goes until about 2014 here, and I would not be surprised if this trend continued to today, where we have literally 10,000 publications using this technique in every area of science per year. So it's growing very rapidly, and the number of users is growing much faster than the number of specialists in this technique. And so I hope to give you an introduction to at least get you comfortable in doing experiment today. And we'll talk about how these experiments are done. My general themes that I would like to cover for you is first, as I mentioned, looking at the structure of materials and what the differences are in a glass versus a crystal. This is one of the most ambiguous problems in glasses, is that we don't know the structure. There's no absolute structural model for these materials, which means we have to do some guesswork. And a lot of the science has been done in the last 50 years by trial and error, which is a great way. But if we want to create the materials for tomorrow, we need to have a little bit more predictive measures. So we'll look at the glass structure versus crystal structures. I hope most of you are familiar with the basics of crystallography. Just knowing what a structure looks like and it's made of atoms, that's all you really need to know. And then we'll step back and look at Raman scattering, what it is and how it's applied to these materials. Then we'll discuss about quantifying the spectra, and this will focus generally on glass spectra because the quantification of crystal spectra is usually almost always quite straightforward. And in the glass literature, if you've read any amount, you'll see that it's quite varied, let's say. Different groups have different explanations for things. So I tried to bring all this together and provide a coherent framework for moving forward. And I'll end by giving a bunch of different examples of how Raman spectroscopy has been applied in many different glass compositions. So at the top of your screen, on the left-hand side, you'll see an arrangement of atoms. This is silicon and oxygen atoms. You can see the central silicon here, the black dots, are linked by oxygen. And we get the sense just from looking at this visual that we can take one of these rings, for example here, and translate it in either direction and form a three-dimensional structure, also including into and out of the page. In 1932, Zachariasen, he described what he thought was the difference between crystalline materials and amorphous materials, that this nice repeating structures we see over here have some disorder. They break apart somehow. They form different numbers of rings. And that was his picture that he published in 1932. It would be another 50 years before any developments were made, and it would be another 80 years before we actually visualize this. And on the bottom are transmission electron microscopy images of a bilayer of silica, and that was crystallized. This group, Huang et al., who published this letter in 2012, they were actually working on single sheets of graphene layers, and they actually accidentally sputtered some silica on top of the graphene, and it happened to produce these beautiful TEM images showing the 6-member rings here exactly as Zachariasen predicted in 1932. They also found non-crystalline regions with different numbers of 5-member rings and 6-member rings here, similar to what Zachariasen had hypothesized. So the first thing I want people to take away is that the main structural difference is not in the small silicon oxygen tetrahedral units here, but in the long-range order. You can't tell to get it means is that the translational symmetry is broken. So you still have a local short-range order or local symmetry, but you don't have the long-range symmetry present in crystals. While we use silica for lots of applications, such as optic fibers, most applications we want to have a more complex chemistry. And so starting from Zachariasen's model, Greaves in 1985, they came up with a modified random network. As you add a metal oxide here to silicon and metal elements, but usually elements from the left side of the periodic table, sodium, calcium, my favorite, barium, you end up breaking up the network. And so these ring structures that are all nice tetrahedron are retained in this silica region. Sorry, what's going on?
Ben, we lost your presentation.
Yes. Is it back?
Yeah, it is. He's on nowhere. Okay, now it's okay. Now it's all okay. I can see.
I do not have. Yep. I just lost my pointer. Okay. So we have the silicate network. As we add modifier or metal oxides to this network, it breaks it up and you get regions where, for instance, sodium, for example, are concentrated. And these were described as channel structures. If you have just a bit, they might form sort of an island here, and as you add more, you might form these continuous channels through the network. That brings us to a sodium silicate network. These blue blobby features are an isosurface of electron density around the sodium. And in any in any liquid, these will be diffusing around. And so some people come to the belief that these sodium channels are constant within the network, and therefore they might be used for sodium migration, for instance, in conductive materials. But they're actually dynamic. They're diffusing around. At the same time, the yellow and red structures, which are the silicon tetrahedra, are also shifting around and diffusing. So this picture, to understand the structure, we sort of divide it into two elements. Those elements which form the network, and these are the silicon tetrahedron, for instance. They almost always have coordination 4, although this can be changed. For instance, boron will form have 3-fold coordination. And these elements usually have a strong covalent bonds with oxygen, and they're the part of the network that remains constant between the crystal and the liquid. The other part of the network, here exemplified by sodium, is described as network modifiers. These break up those rings and create depolymerization ultimately, but they typically have high coordinations, 5 or above, even 8, sometimes up to 10 or 12 if the element is something very large, such as barium or lead, for example. It's important to remember that these are not hard and fast distinctions. There's sort of a gradation related to the field strength of these elements, formers. And in between both of these elements are the oxygen. So the oxygen, when I talk about silicates, what we're really talking about is oxide glasses and that are bound to both silica and these modifiers. One of the ways we describe how the tetrahedra are linked together is by their connectivity. And the nomenclature for this is the QN species nomenclature. A Q just refers to a tetrahedral species. It could be, as I said, anything: phosphorus, silica, boron, etc. And N is the number of bridging oxygens around that, around the tetrahedron, around the central silica. If we look at the bottom of the screen here in the Q2 species, there are two types of oxygen, a red one and a pink one here, or flesh tone. The red oxygen are bridging oxygens, so you would picture another tetrahedron bound here and another tetrahedron bound here. And these are non-bridging oxygens, so they're not linked to another tetrahedron. So they would be surrounded by the modifiers. These oxygens having a negative charge of about 1, they need an alkali, or two of them need an alkali earth to maintain charge balance. So any tetrahedra can be surrounded by any number of these 5 configurations, from Q0, where there's no tetrahedrons connected to the other, 1 connection, 2 connections, 3, or 4. An example of a Q1 would be these guys in the center of the graphic here. In the two-dimensional depiction of the network, you have a tetrahedron with 1 corner shared to another tetrahedron. Each of these would be Q1 species. On the other hand, you might have 3 linkages. So here's a central tetrahedron. It is connected to 3, 1, 2, and 3 tetrahedrons, so we call this a Q3 species. One of the topics that's become really important, or potentially important, in the last 5 years, say, is that these bridging oxygens, while they have a -2 charge, and so we would think of them formally as when they're shared between 2 tetrahedrons, that their charge is balanced. Actually, in minerals, they have sodium and modifier ions bound to them. So the formal charge is less or more than 2, depending on the situation. How much of an effect this is in glasses and melts is unknown, because this has basically not been studied, though, as I mentioned, it's starting to be studied. So this is a sort of a hot topic that will hopefully lead to new insights about how to make better glasses in the not-too-distant future. So just to reiterate, we can describe how many linkages between Q species are by this QN nomenclature, and we're going to use this a couple times throughout the presentation, so it's good to be familiar and jot this down. One of the things about Raman spectroscopy, here's some spectra here, don't worry about all the squiggles, but I just want to point out that these peaks that we see, quite intense features, are related to that connectivity. So this is the link between Raman and glass structure that I'm going to talk about more for the rest of the conversation. Before we get into the details of those Raman signatures, I just want to look at glasses for a second. This is a broad list of glasses put together by Charles Lalas from last year in his review chapter. And on top here are natural glasses. Here is optical fiber. Here is Pyrex. Here is nuclear waste glass. These are some ancient glasses from Babylonian, Egypt, and the Middle East in here. And if we look at their compositions, the bars represent the different elements. So gray is silica, and you can see that in optical fiber, for instance, are basically pure silica. But most other natural and synthetic glasses are made of some mix of silica plus aluminum plus magnesia, sodium, potassium, with some other minor elements, for example, titanium, boron, or lead in the case of this glass here. So a lot of efforts have been made to understand simple binaries with just silica plus one of these other elements, and that gives us the structural insight to feed into these more complex compositions. So I'm going to talk about a lot of binaries examples today of silica mixed with something else, because this is where we have the most control and we have the least influences between the chemical species and the reaction between the cations themselves. In case people are not familiar, I've introduced this QN nomenclature. But if we look at the graph on the right-hand side here, this shows the broad structural hierarchy of silicate minerals. For TiO2, these Q4 systems here, if you're a mineralogist or crystallographer, you might refer to them as tectosilicates. A more generic term would be frameworks. They typically have almost all Q4, or essentially all Q4 species, and they have high silica contents, upwards of 80%. Next we have the disilicates or sheet structures. You can see here, also in the mineralogical world, termed phyllosilicates. They have this sort of a broad range of compositions from 50 to 100%. Then chain structures made by Q2s. If they're wrapped in a circle, we might call them ring structures, but if they're extended chains, we call them metasilicates or inosilicates. And these go down, as we mentioned. You have the Q1 sorosilicates and Q0 nesosilicates. In terms of our glass forming range, typically the traditional range is forming silicates with over 50% silica. And now with modern process techniques such as laser heating, we can form glasses with really high quench rates where we have Q0 and Q1 based glasses. So that's how the mineralogical, the glass, and the compositional realm link to the QN species here. And I just want to highlight at this point that the number two fundamental difference between the structure of glasses and minerals or crystals is that in the liquids or glasses, you have some distribution. You have multiple of these QN units, usually at least two, if not three or four, whereas 90+% of crystals have only one type of QN species. So when we're thinking about our structural modifications and design of glasses and glass ceramics, we are looking at the change between this distribution of QNs to one single type of QN units. And that's what we're going to be discussing today. If there's any questions at this point, and if Maziar, you want to restart the video or recording, I think there is a slight hiccup here. Feels free to go ahead.
Yeah, Ben, we don't have any question, written question, but first your screen has freezed. Please restart your webcam, your webcam, we don't have you. So then I need to ask the audiences if they have any question, they can write it down. A quick question. This is the first break of our presentation about the structure of the glass. If you have any question about the structure of the glass, please ask the Ben. Ben, also you can raise your hand and I can turn on your microphone, then you can discuss with Ben.
Perfect. Okay. Before I go any further, I just want to let everybody know I'm going to be posting, or Maziar is going to be posting the slides for this talk online afterwards. So don't feel free, I might be throwing a lot of information at you, but don't worry about getting overwhelmed because you'll have access to this later on.
Okay. Ben, please turn off. Someone wants, just let me. No, I missed. Someone raised their hand, I missed the red microphone. Please talk. I don't remember your name. Please, I turn on. Any question we have?
Okay.
Question? No, we don't have.
Don't worry about it. We'll have another opportunity.
Just turn on your webcam, please. Okay.
Okay, is that going?
Yeah, go ahead, please.
Okay, so if this is new to you, I highly recommend that.
Yes. Still you are freezed. Can you, just restart your webcam or something? Just close your webcam, please. Share it again.
Sure, doing it.
So no, there is a problem somewhere. I don't know. Maybe it's the
Okay,
speed or something. You don't know. Need your cam. Okay, you
good
can
to
go on.
know. So long as you
Yeah,
can hear me,
yeah, it's
my
okay.
voice will have to be enough.
Yes, sure.
So, uh, as I was saying, anybody who's interested in this glass structure and wants more details, Henderson has this article from 2005 that really goes into a lot more detail about the concepts that I've introduced here today. So let's turn to crystalline phases. On the left-hand side of your screen is the unit cell of the mineral sandbornite. Sandbornite has a relatively simple composition in barium disilicate here, BaSi2O5. And it's a Q3 base phase with sheets of tetrahedra that extend in 3 dimensions, and they're separated by these large barium atoms. And so you probably know that, or are familiar that Raman is fundamentally probes the vibrational modes of these crystalline materials. So for any crystalline phase, it has 3n minus 6 vibrational degrees of freedom. Why do you ask minus 6? Well, minus 6 are the translational or rotational pure translations and pure rotations. So if the whole unit structure moves in the same direction, whether by rotating or translating, there's no actual change in the move there's no actual displacement of the atom. So each of the atoms in the crystal structure can vibrate in 3 normal directions, the 3 Cartesian coordinates, x, y, z, for example. And that gives us, if we do the math here, there is actually 4 compositional units in the unit cell of a sandbornite. So that makes 3 times 8 is 32 atoms in the unit cell depicted here. And those, if we multiply by 3 for the 3 Cartesian coordinates, minus the 6 pure translations and pure rotations, we end up with 90 vibrational modes. And Raman spectroscopy gives us access to some of these modes. If we step and just consider a pure diatomic molecule, such as a silicon-oxygen bond, as they move away from the minimum condition, as you stretch them, they will gain some potential energy. And we can sort of model this, the expansion and contraction of this bond using Hooke's law. And that tells us that the frequency of these motions or vibrations is related to some constants here, pi and the speed of light, multiplied by the square root of k over mu, where k is the force constant, and you can think about this as the strength or covalency of the bond if you want, and mu is the reduced mass, which is the sum divided by the product of the mass of the atoms involved. So we describe these vibrations by their frequency, and collectively we describe them as phonons when they're in a material. And so when we talk about the phonon or vibrational density of states, it's all the frequencies of all the different vibrations in our phase, whether crystal or glass. So how does Raman spectroscopy actually work? Above is this ungodly equation here, but just briefly, when you shine light into a glass or a crystal or any material, actually, some of the light can be reflected off the surface. Some is transmitted through the material. Some can be absorbed, but some is scattered. And so what happens when a photon of light, a light particle, enters into the material? It interacts with the electron cloud in that material to produce some change that we call an induced dipole. When scattering happens in this process, you can have 3 different situations. So the photon comes in, it hits the vibrational state here, ground state. They interact and create what's called a virtual state that happens on the order of picoseconds. And this instantaneously, or at least as experimentally instantaneously, decays and releases a photon that scatters out of the material. If these photons interact with the phonons and scatter at the same frequency that they came in at, we call this Rayleigh scattering. And so there's no change in energy. Whatever the energy is in here, we call zero, or the E naught. If there's no change in frequency, we call this Rayleigh scattering, and this front term in the equation describes Rayleigh scattering. However, sometimes when the virtual state decays, the outgoing particle has lost some energy. It's interacted at a higher state here, and so it's lost some bit of energy. And that loss of energy is where the frequency change happens and where the Raman effect takes place. So in the Raman effect, there's sort of two flavors. There can be Stokes scattering or anti-Stokes scattering, where the photon have lost a bit of energy or gained a bit of energy. And in the anti-Stokes case, what we're actually seeing is that the vibrational phonon was excited to begin with, and during this the photon-phonon interaction, we decay back to the ground state. So it's gained some extra bit of energy and therefore has been blue shift to higher energy, producing these modes here. So you don't have to worry about all the details, but essentially how much this shift is, whether it's Stokes or anti-Stokes scattering, corresponds to the different frequencies of the vibrational modes. If we look at this equation, there's some coefficients out front, and I want to highlight one in particular. If the ability alpha, so alpha is the polarizability, and we want to look at how this describes how strongly the photons of the visible light interact with the phonons in the material. So if there's a change in the ability to polarize the material, and a change in the displacement, which is just having a vibration, if this factor here is non-zero, we get the Raman effect, and we can have either Stokes or anti-Stokes. So the base selection rule for Raman is that this quantity, delta alpha over delta Q, cannot be zero. And these shifts, as I remind you, are related to the frequency of the vibrations we just looked at. To put that in a little less mathematical and more figurative terms that are probably easier to make sense of, at least they were for me, here's a simple molecule of CO2. And there's a couple different vibrations here. On the left, you have the two oxygens stretching away from the central carbon and returning. So this is described as a symmetric stretching, a vibration. And in contrast, we have another vibration with a different frequency where one bond is compressed while the other is extended. If we just look at the center of charge of this bond, we see that the center of charge stays constant, and this remains, we describe as having a constant dipole. In the case of the symmetric stretch on the left here, if we drew an ellipse of sort of the electron density, and we relate this to how well it interacts with the incoming photons, we can draw sort of you can imagine an ellipse here that's larger when the bonds are stretched, right here, and smaller when they're compressed. And so this change in the size of this ellipse, we call the polarizability ellipse, is what allows for a non-zero solution in our coefficient here. This means that as a result, this vibration here is what we call Raman active, so we will see a peak in our spectra that we can assign to this vibration. And on the right-hand side, we see that the center and negative charges are shifting with the vibration, but the same shift is to the left or right, gives the same size in the overall sphere. So there's no change in this quantity, and the coefficient here, alpha over Q, is constant, or is, sorry, zero. And so this mode will be Raman inactive, but it will be accessible by IR. And I won't get into too much details with IR, but except to say that we need a change in the polarizability with a change in the displacement of the atom to see the Raman spectrum. For those of you who are totally new to Raman, and for those who want a little review, we look at relative wave numbers. Here is a spectra. In the left side of your screen, we have some intensity that we record on our detector, and we have some scale of frequency. This is reported in frequency sometimes, it's reported in wave numbers, in inverse centimeters, or as Raman shift. And it's important to just remember that this is shift in wave numbers, inverse centimeters, relative to our incident laser light. So we can describe the incident laser light. For instance, if we have a green laser, a 532 laser, you can do the simple math to convert nanometers to inverse centimeters, and you'll get this value here, 18,800 or so. But there's actually the light that scatters without shift. This elastically scattered or Rayleigh scattering light will have zero frequency shift. So we need to have some filter, because we don't want to look at that Rayleigh light down here close to zero. If we had a vibrational modes, for instance, a peak here at 1,000 inverse centimeters, we could calculate what the wavelength of that vibration is by knowing, by plugging this 1,000 inverse centimeters into our formula here, and we would see that this band correlates to a wavelength of 562 nanometers. So we have red shift to longer wavelengths as you increase the Raman shift, and you have to shorter wavelengths going at negative numbers in the typical Raman spectra. We mentioned a moment ago that there is a mass effect, and if we have a larger mass, that we should decrease the frequency. And this is exactly what you see here. These are two crystals, calcium magnesium germanate, and a calcium magnesium silicate. And they are isostructural. And we see that in the silicate on bottom here, the frequencies are shifted here by about 100 wave numbers, here by a little bit more than that. And we see a smaller shift, but still a shift nonetheless, in these peaks down below. And so I want to make 2 points here. One is that the masses do have a strong effect on the vibrational modes, which means you can use this if you have substitution, for instance, of iron for magnesium in your phase. And two is that even with quite different compositions, if they are isostructural, you can transfer insights from one structure, for instance, germanate, to a silicate, if they have the same profile. And of course, there's some other subtle differences, but we will take it easy for a moment. To determine exactly which peaks correspond to which vibrational modes, it's quite involved, and there's no simple answer to it. It depends on the symmetry of the crystal or molecule and how the group theories and factor groups play into that. So what I find is that a lot of Raman books in particular, they go a lot into this part of the knowledge required to understand the spectra, which is really important. But it's quite involved, and it's not very practical for a lot of practitioners like myself. So I will not talk about group theory anymore. I will tell you how to interpret these modes in a minute. And I will focus on the practical applications of what to consider in doing a Raman experiment. So just to show you that whatever light you have doesn't really matter, these are three spectras of the same material here, Celsian, and they have a bunch of peaks. We describe these vibrational modes as peaks or modes or bands, depending on your philosophical perspective. But if we shine a blue light or a green light or a red light with these wavelengths, all the vibrational modes stay quite constant. So this tells us that indeed the relative shift here, the Raman shift, is independent of the wavelength of light. So all of these bands are faithfully vibrational bands. If you change the source and you get a shift, for instance, this band comes over here, it's probably not due to a vibrational mode, but related to fluorescence or some other type of, for instance, electronic transitions in your material. So it's good to always test just to make sure that what you're seeing is vibrational modes and not other things. Now, at this point, you might be saying, well, oh my goodness, look at all these peaks. It's hard for me to make sense of this. There is so much going on. So how do I determine what vibrational modes are in a given phase? And luckily for you, Barbara Lafuente and Bob Downs at Arizona State have created an open, free database called the RUF database, and it has 14,000 high-resolution Raman spectra of various crystals, from phosphates to carbonates to silicates and much more. And they also have diffraction data and chemical analysis associated with these mineral phases. And so they're in their RUF project, they have developed a software that if you take a spectrum of an unknown sample, you can search through this database and it will tell you what are the highly probable phases in your ceramic. But generally speaking, after you get a bit of experience, you'll see that the most intense features are quite distinctive for the different groups. This figure from Freeze and Steel shows that, chain silicates typically have bands here around 1,000. Carbonates are a little bit higher, organic carbons even higher. CH stretches and water bands are at even further removed wave numbers, up to 3,000. And so it's not that bad, actually, once you get a hang of, or get some familiar with the different phases, determining what you're actually seeing. But how do you do it? So you can do it the hard way, as I mentioned, with group theory, looking at all the symmetry elements, and you can do some specific Raman experiments called polarized Raman, and determine which symmetries correspond to which bands and make an assignment. That's great, but I will tell you there's not so many groups who do this. Most people find peak assignments from other authors published in the literature. As I showed a moment ago, phases that are isostructural should have similar assignments to them. So you can also use silicates as a guide for phosphates or germanates. This works to some degree, but with all the subtleties, it's not the best strategy. The final way to determine what the vibrational modes are you're seeing is to actually simulate the vibrational frequencies. The other database that's currently being developed, that is again free for everybody, open access database, is the Raman Open Database. You can find it at the SOLSA website down below. This is currently under development. So there's, as of last year, the middle of last year, there was only a couple thousand entries in the database. It's being developed by the International Commission on Glass, specifically by the Technical Committee 26. And I happen to be a member of this technical committee. So I hope this database grows as folks like yourselves contribute spectra and good quality studies to this so that everybody can have access to them. I mentioned about simulations. You can have various ab initio first principles calculations of the structure. If you have a molecule or you know a crystal structure, you can actually build up that structure from the molecular orbitals themselves and determine with a fairly excellent degree of accuracy. Probably the most well-known and broadly used is the crystal program. It's great for crystals, but it's not so good for glasses and other types of networks. This is one that I have worked a little bit with, but there's other options such as the VAST package or Quantum Espresso or Travis. So know that there are options where you can plug in the crystal structure if you know it and determine exactly the origin of the vibrational modes. I have done this simulation with some colleagues in Spain, and just to show you an example of a nice sharp vibration from our crystal sambronite we saw a moment ago. I tracked this with temperature, and we knew how the thermal expansion of the crystal was. And so I was able to determine a very strong relationship between the SiO1 bond length, this bond right here within the structure, as a function of temperature. So once you know, if you have simulations, it's really powerful because you can identify specific attributes within the structure, such as specific bonds, and create some empirical models of how they change with pressure, with temperature, or during other reactions. If you are looking at the literature, there's a broad range of vibrational modes that are described in various forms. And I want to show you the vibrations here because it's often difficult to visualize and understand them if you don't see them in motion. So in solids, you will see various wagging vibrations, torquing or twisting, what's been described as rocking vibrations here. Bending vibrations we've seen, asymmetric and symmetric stretching vibrations, which we showed a little bit a moment ago. In the solids, you have symmetry, and you have symmetry of the local configuration of the elements. But in amorphous solids, we saw that you lose translational symmetry. And so as a result, we need a different way of describing the vibrational motions. And there's a growing consensus that the best way to do that is by vibrations that are in and out of the plane. For instance, here you have silica between two oxygen. If you have a motion in and out of the screen towards you and away from you, we describe this as a rocking or an out of plane motion that is along Z. If you have motion within the plane, in the XY plane, relative to your different atoms, we call this bending. And if you have a compression or expansion of specific bonds, we describe this as a stretching mode. So we'll come back to this a little later on about how this is applied in glasses and crystals. But all of these are possibilities. If you go back in the older literature, I caution you because these terms aren't always used rigorously from publication to publication. In general, the frequency of these modes increases from left to right across the screen. So with that introduction to vibrations, I want to turn next to what is involved in a classic Raman scattering and some of the more technical aspects that you might need to consider before doing an experiment. What happens is you have light scattered off the sample, and it is goes through a filter that rejects that elastically scattered light because we don't want the Rayleigh scattering. There's no vibrational information there. So it's filtered out the Rayleigh line. Then a lens focuses the scattered light, onto a grating, and this grating allows us to separate the change in frequency. So, red, green, blue light here. And that's ultimately, that light is read by some sort of detector, and we get some peaks in our spectrum. All you need is scattered light from the material. So one of the reasons it's blown up in popularity is that Raman can be used on anything, liquids, solids, powders, gases, inside a reaction cell, you name it. Your imagination is the limit so long as you can get visible light from the sample onto your detector. Some of the most common lasers used are blue lasers like the 488 or 515, down to red lasers like the 633, or infrared and near infrared lasers such as 1064. Powers range from 0 to 500 milliwatts. As you go to longer wavelengths, we'll see that the Raman response decays. So you need to increase the power to make up for this lack of response. And you can do several different types of geometry. The most common for silicates and ceramics is in the backscatter geometry. So in general, these different color wavelengths of incident lasers are used for different applications. Blue-green lasers are excellent for silicates, and you will see almost always green lasers used, but also blue. They're excellent for ceramics that you're probably interested in, but they're also good for other types of more advanced Raman experiments, which I'll leave for another day. Red and near infrared lasers are excellent for fluorescence suppression. They're also good because of their low intensity. They don't tend to damage fragile samples. So when you're making an image or map, like I showed at the beginning, you can use these wavelengths so that you ensure that there's no damage and you're getting actually the vibrations of the material, not the damaged material. Finally, ultraviolet lasers are great for DNA and RNA samples. I am not so familiar with those, so I will leave that if you have any questions for the research on that. Intensity is a bit of a complicated variable in Raman scattering measurements. It is proportional to the fourth power of the frequency, the incident power of the laser itself, how many number of molecules or atoms you're exciting, and to the square of the polarizability here. So one of the problems with Raman scattering is that, especially in glasses, we don't know how polarizable the different vibrational modes are. This leads to distortion where a lot of people focus on the very intense peaks, but they may not have the information we need. One thing to highlight here is that because the frequency goes to the fourth, if you have a higher frequency or shorter wavelength laser, the intensity of your signal is enhanced. So if you have a really sensitive sample, or you need to only analyze for a small amount of time, you want to go to the blue end of the spectrum because it will greatly enhance your intensity. One more note on intensity is how we normalize it and how we present the spectra. Here on the left hand of your screen is a bunch of glass spectra that goes from pure silica to 50% sodium. Pure silica is here shown in black, and you can see it's very weak and only gives you 200 counts for the experimental conditions where this was run. But as you add more sodium, you'll get a much higher intensity. And this is related, these differences are related to that polarizability I mentioned a moment ago. But so if you compare all these spectra just by their raw intensities, you come to some very misleading view of what's happening in your sample because the intensities are so different. This has the 50% sodium sample has 4 times the intensity of the pure silica. Normally what you do is some sort of normalization, either area normalization or I recommend intensity normalization, where you make the maximum intensity equal to 1, and then you plot the spectra offset. So you can see the vibration here is equal to the vibration here, and you can get a much better comparison of how these peaks shift and grow or do not grow as you change the composition, for instance. One of the other aspects of the intensity is if you're working with high temperatures, you see this is an experiment at 700 degrees Kelvin, 500 degrees for a lithium borate glass. What happens with high temperatures, you get a huge enhancement of the low frequency part of the spectra. You get a gigantic wing here. And people thought, or people still think, that this is related to those ground state vibrations, and that as you increase the temperature, you increase how many excited vibrational modes are interacted with, and you get this enhancement. So to get rid of this enhancement due to the vibrations not being in the ground state to start with, you can divide your observed intensity by the Boltzmann distribution given here, and you see that the temperature is on the bottom, so you'll end up reducing it, and you'll get a spectrum like this. There's many other intensity corrections out there, for instance, long correction. But the problem is that at low frequencies, you see this peak. It may not be just coming from the vibrational population, but it's coming from actually a feature called the boson peak. And so other temperature corrections actually eliminate this boson peak, and there's some other peaks under here, not readily seen in this spectra, that were eliminated. And so one thing, if you get to reducing your spectra by more than a simple intensity correction, such as I presented, you'll end up eliminating these peaks and eliminate information from your spectra. And this to me is a loss of an opportunity. So I just use a simple reduced intensity. Another very important variable is the actual volume of the scattered light you're looking at. And you'll see in many, many papers report a resolution, lateral resolution of a micron. That lateral resolution is determined by this relationship here, where 0.6 times the wavelength of the incident radiation divided by the numerical aperture of your objective. So just for argument's sake, I've put our green laser 532 with a 50 times long working distance objective that has a numerical aperture of 0.35. And you can see, indeed, the lateral resolution is about a micron. And I've actually hit waveguides that are a few microns thick and seen that, indeed, this is true. You do have, can get a lateral resolution of a micron. But what that doesn't take into account is all the scattered light below the surface of the material. And to get that depth resolution, or the actual resolution, this is actually determined by 2 times the n here is the refractive index, times the wavelength again, divided by the numerical aperture squared. So if we use the same conditions as our previous calculations, but on a glass that has a refractive index of 1.6, we have a vertical resolution of about a vertical volume of at least 14 microns. I highly recommend that you put this information in your publication, but I warn you that this is a gross underestimate and that the true sampling volume, because of the scattering below the surface of the sample, is not actually a cylinder, but it's a cone, then it can be much greater than this volume. So volume, if it's important, or depth resolution, if it's important to you, I recommend getting a laminated film and testing based on your experiments how deep you can see which of these materials. And you can play around with the pinhole and the surface of your sample to improve this resolution. Generally, smaller pinhole, smaller refractive index, the better resolution you'll have. Ultimately, all the things I've just talked about combine to determine the quality of the spectra. So your experimental conditions, the quality of your detector, the grading, all the lenses, the confocal hole, the wavelength of the incident of radiation, the surface of the sample, the color, how homogeneous it is, and the refractive index have an influence on your spectrum. The spectra shown here on the right-hand side is quite noisy, and I probably wouldn't publish this spectra if it were me. I'd spend the time to take a little bit more, a few more spectra and average them out to get a reduction in the signal to noise. But it depends on what you have and how much time you're willing to spend in the process. At the end of the day, the advantages and disadvantages of Raman spectroscopy are the following. Almost any material, glass, liquid, gas, liquid, solid, can be studied. It has, with a very short amount of time, excellent spatial resolution, lateral resolution on the micron scale, and depth resolution of several tens of microns, usually. It's non-destructive, so long as your laser power isn't too high and you don't have a lot of absorption. You won't damage your sample. There's absolutely no preparation required, although if you polish your sample, you will get a better signal to noise. You can take a very good spectra with a high power laser in seconds and for sure in minutes, depending on the nature of your sample. As I mentioned, you can use in situ devices for reaction cells, pressure, temperature. So long as you have a window that allows visible light to pass through, you can do in situ Raman measurements. And I just put another pro here that it's much more sensitive than X-ray diffraction. Any substitution, any distortion of the symmetry of the configuration of the elements will produce a change in the peaks. And so it's typically much more sensitive than XRD, and in fact, I would argue many other techniques. On the other hand, and we'll discuss this more in a moment, it's rather difficult to quantify. It's not good for fluorescence samples. So if you have manganese, for example, where there's a lot of electronic transitions in the visible range. It fluoresces very strongly, and you won't see any of the vibrational modes. Usually, in a good study, it's best to have two different techniques, whether it's Raman plus NMR, XPS, or infrared, to get the whole picture of to get a consistent picture of your system. The last two cons here, I'm going to talk a little bit more, but there's quite inconsistent data treatment in the literature, and so to compare between studies, you have to apply the same data treatment that they applied, or you can't make a really rigorous comparison. And as a result of these inconsistency in data treatments, the interpretations that are produced, even for the same system, are sometimes completely different. And I'll talk about this in more detail as we go. For those of you who are not spectroscopists, like myself as a geologist, I think it's important to stay focused on your goal. If you know a study what you want to do and you want to reproduce it for your samples, keep focused on what that goal is and learn everything you need to achieve that goal. And I highly recommend, because it is such a growing and powerful technique, that you keep doing new experiments and gain from the experience as you go. It will open doors and open your eyes to lots of new information and insights about the materials you're working with. So I'll just take a step back for a moment. If there's any questions, Miser, let me know. But I highly recommend, for people who want a more detailed introduction, check out Max Giam's book, Modern Vibrational Spectroscopy. Unlike a lot of other books I mentioned, he focuses on a lot of practical components that we've mentioned here.
Yeah, thank you very much, Ben. Yeah, there was one question, but I think you have already answered the question. It was about the sample preparation. If you want to comment more on this question, the sample preparation, any specific preparation is needed. You said that if the polishing, but if you want to comment on it, please do it.
So there's no required preparation, but if you polish the sample, it's always better, because the scattering, when scattered light comes from inside the sample, if you have a rough surface, it'll scatter the light to the sides, and so you reduce your signal. So it's always better to have a polished sample, but there's no specific preparation you need to do.
Yeah, there is another question. Then Emmanuel has a one question. I am having trouble to collect Raman spectra from silicon clay samples. How could I approach to solve this problem? I am using a 532 and 785 laser and Redshift equipment. I don't know the name of the equipment. Did you understand
Great. Thanks for the question, Emmanuel. So if you're using powder, you suffer the same problems with having a rough surface, which is that you get scattering in all directions. So one of the tricks I use for powder samples is to tamp down the powder so it's sort of packed on top. If that won't affect your sample preparation, that packing will align the flat surfaces with your spatula and allow you to get a better spectra. The other thing that happens a lot when you're dealing with silica and clays are kind of messy materials. I've worked with them myself. They are weak scatterers in general. So if you're used to simple crystals, I can take a crystal spectra I showed you there in about 10 seconds. But for powdered amorphous samples like silica and clays, you might need to take a much longer spectra. So for me, I would suggest try a 10-minute spectra. Take about 12 different spectra, 12 accumulations with a dwell time of 10 to 30 seconds, and try taking a longer collection. That'll give you this weak, better resolved signal for amorphous and poorly crystalline materials like clays. So try those things. And I will include my email at the end of the presentation. If you want to email me afterwards, we can discuss further. I'd be happy to. So let's go to our glassy spectra and how we deal with these beasts that I've been saying are so difficult to do. So in a nice review chapter here by Professor Alameda from Spain, his conclusion for the chapter on Raman spectroscopy of glasses was the following. In conclusion, there is no single theory for accurately predicting the first-order vibrational spectra of glassy materials. Composition variations, whenever possible, are very helpful in assigning the peaks and interpreting the glass spectra. So this is true. There is many approximations that you can make to predict the glass spectra, but we honestly don't know. We don't have a single theory that accurately predicts all the scattering effects that we observe. This makes them for a bit of a messy subject to deal with, and this is what I was mentioning. This is ultimately what underlies the fact that you have different interpretations and inconsistent interpretations in the literature. So I want to, my take on this is that while we don't have a single theory, we can use analogies between crystals and glass to constrain what will be a reasonable interpretation. And I'll define what reasonable means in a minute for me. And I leave it to you to decide if what I think is reasonable for you. So, starting with the most studied glass by Raman spectroscopy, here is a spectrum of silica. And you see that at low frequencies, below 500 or 600 wave numbers here, you get this really big broad feature. This is described for most of the literature as the main band. We mentioned earlier that at low frequencies are the bending and rocking modes. And so most people assign this to these, but we really have no way to tell because it's a very broad, featureless envelope that anything could be under there. At increasing wave numbers, we see two sharp features, these guys here. The consensus in the community, and this is just defended by simulations of Saranthian in 1997, is that these modes correspond to the breeding modes of three-member, here's three-member, and four-member rings. These are tetrahedra of silicon and oxygen between them. And in the four-member ring and the three-member ring, all the oxygen move away from the center one of silicon. Above 1,000 wave numbers, we have two broad, low-intensity peaks that are assigned to the T2 mode. And in this, the tetrahedron has opposite edges. Here's one edge, here's the opposite edge, that compress and expand as inversely related to the other. So one expands and one compresses. And this is related to those Q4 species in the network that we were describing earlier. So that's silica, but what happens when we add some modifier oxide into the mix? When you add just 5% sodium, the spectra stays roughly the same. These are offset, but you can see that the shape of the envelope is pretty much the same. We see the D1, the D2 bands here. We see this cage rattling here. What you get is a slight difference in intensity around 900. And you get a very strong peak that appears at 700. It is at the high frequency region here, and not too much of a shoulder, if any, on the low frequency side. So something about adding sodium changes the polarizability of the vibrational modes. Or we have new vibrational modes as well. You have those two options. Some people would argue that in aluminosilicates and even in silicates, that these T2 and A1 modes are found in these sodium-bearing silicate glasses. I would say that something happens here to change the intensity of this band, causing it to become more polarizable and therefore more intense, and that this shoulder at high frequency, extending above 1200 wave numbers, is probably the same as the A1 mode. But as we see no shoulder on the low frequency side, this T1 mode doesn't appear to be present in this band. And of course, if you have sodium influencing the oxygen, you might not get the motion that's associated with this mode. Other people argue that in all cases, at all times, this T2 and A1 bones are there. Either is acceptable, but I think that that the A1 is present and the T2 is probably not present, based on this comparison and others. So that's the main difference. There is some change in polarizability that strongly affects the high frequency region when you add something else to the pure silica network. This insights about silica were at the same time accompanied by insights about the other silicate compositions. This is a seminal paper by Brower and White, and even by today's standards, this is an excellent paper. They compared glasses and crystals of the same composition. Here we show on the top sodium silicate glass, and on the bottom the crystal. Here a potassium silicate metasilicate glass, and on the bottom the same crystal. What one can observe is that the main intensity features, so for instance, this peak around 970, 980, this peak around 600 wave numbers, and this peak here around 300 or 400, there seems to be the same vibrational modes in the crystal and in the glass, but there are some differences. Excuse me. For instance, this peak is quite a bit broader than the peak in the crystal. Same goes for this peak. We see that the peaks in the glass are significantly broad, and we also see some extra peaks in the glass that are very weak or non-existent, for example, here in the crystal. So there are many similarities, but some differences, and usually the differences produce more vibrational modes in the glass spectra. I highly recommend people read the Brower and White article. If we broaden, so that was an example of the metasilicate composition here at 50% silica. If we look at a compositional suite, this is in the barium silica system, which is from my current work, we see that the crystal structures here, disilicate composition is composed of Q3s, the metasilicate here is Q2s, and here's the orthosilicate with Q0s. And in the high frequency region, we see strong peaks related to these structural units that sort of correlate similarly. They sort of bound the peaks in the glasses. And this persists, for example, these Q2 peaks appear in the glasses even as low as 30% or 40% barium, 45 or even 50. So there's a whole trend going from Q3s to Q2s. Maybe there should be a Q1 in here somewhere to Q0 between the glasses and crystals. And this is also true of these lower frequency modes as well, except that they're quite a bit broader than the crystalline vibrations here. And you see that for some reason, this low silica or high silica barium silicate glass here with 29% barium has sort of a doublet feature, but once you get to 45, it seems to have got rid of this, the peak that was here. So there's some very close similarities, and it seems that the glasses are following the general trends in the silicate crystals, but that there's some significantly broader and some subtleties between them. In a simulation study, they took the glass, sodium disilicate glass, Kilimis et al. Simulated the vibrational modes based on some assumptions. And if you read some of the older glass literature, they usually equate all of the low frequency modes with SI bending, and therefore these modes are related to bridging oxygens between two silicon tetrahedra. And this is separate from the high frequency region above 800, where the vibrational modes come from silica NBO vibrations. This is the standard picture, and the reason it was thought that NBOs are important is because they're only bound to one silica. They're not bound to another silica covalently on the other side, so they're free to vibrate more strongly, and it was thought that they were more polarizable. These simulations, and this is consistent with my own work on a variety of crystals, here the vibrational modes are divided into the contributions from bridging and non-bridging oxygen. And you can see there's a variation across the frequencies. But for any given frequency, the contribution between bridging and non-bridging oxygen is roughly equal. So these old paradigms, these old simplifications are probably a gross oversimplification. And if we want to get to a more realistic structural model, we might need to reconsider this paradigm. But we can not only divide by bridging and non-bridging oxygen, we can divide by the motions we talked about earlier. So in their simulations, again, from the same study by Kilimis from last year, if we divide the motions by rocking, bending, or to the bottom here, we see that from 0 to 800, we have intense region from 0 to 400 with a lot of rocking. That continues to 800 wave numbers. The bending shows the inverse behavior, where it has moderate contributions at low frequencies and then increases the contributions in the center of the spectra. Both of these become almost zero and don't contribute to the stretching region above 800. So these stretching motions, where we saw those QN bands a moment ago, are really, they don't have any mixing, so there's less ambiguity about the origin of these frequencies, but they basically dominate at higher wave numbers. These generalities are true for crystals and glasses, so you can apply to almost anything. Just remember that if you're changing the mass, you will shift these frequencies. If we break the simulations, the vibrational modes down instead of by motion or oxygen, but by element, we have the graph produced on the left here. On the top is silica, oxygen, sodium, and I invite you to note the scale here. This goes to 0.4. 0.4 is down here quite low in both of the bottom two panels for oxygen and sodium. So what's important here is that silica motions contribute across the spectrum, but in low intensity. Oxygen is the most intense feature at almost any frequency except perhaps around this 800 band. And finally, sodium contributes only to vibrational modes below about 400. As I mentioned a moment ago, if we have an increased mass, such that we put barium or lead in our glass, the vibrational modes will be severely enhanced at even lower frequency. And this creates that issue with intensity corrections I noted at low frequency. The important aspect is that in all cases, oxygen is the thing that Raman spectroscopy probes strongly. And so it is changes in oxygen almost ubiquitously that are the strong changes in the spectra that you will observe upon measuring it. I mentioned that these stretching modes are quite consistent. We mentioned a similarity earlier, but let's look at some crystals and an early correlation from 1984 that compared the intensity of the main feature in crystals where the structure was known, Q4, Q3, Q2, Q1, Q0, and compared it to glasses, the most intense peak in the glasses, and they found that both crystals and glass have a very similar behavior, and they're combined into this relationship here, where the frequency decreases as the number of non-bridging oxygen increases, and the separation between these frequencies decreases as well. So the separation between Q0 and Q1 is about 50 wave numbers, whereas here between Q3 and Q4, it's close to 100 wave numbers, perhaps. So there's quite a strong change in the frequency that is existing clearly well correlated between glasses and crystals. And this makes that qualitative assertion that there are similar vibrations stand on much stronger evidence. I have recently redone this for all 160 different crystal spectra. This is work that's currently under review. And these crystals have a large variety of symmetries and composition. And despite the potential for total chaos in the vibrational modes, we actually see quite consistent ranges here shown and plotted as a function of their oxygen to silicon ratio. So 4 MBOs will be Q0, Q1, Q2, Q3 here. And we see that there's the same frequency shift observed for the 25 crystals, but for a much larger range. And I've given some bounds on what the expected values are. There is a little bit of overlap you can see between the extremes of these frequencies, but there is quite a systematic trend that can be found if one looks closely enough. So just to summarize what types of vibrational modes and what we've seen so far, for crystals, it's much easier to do to make simulations and to get a discrete assignment for the mode and where it originates from. And this allows us to have a much higher sensitivity, not just because we might know where the mode comes from, but because it is much finer and therefore changes to its frequency can be controlled under stress, for example, or other deformations. I've convinced you now that there's some relationship between the frequency of the vibrational modes and things like the QN structures, the bond length, some ring structures we've seen in the sorrel silicates, and that these relationships remain to be developed more rigorously. In glasses, we've seen some ring structures as well, the D1 and T2 modes. We've noted that the low frequency region is related to bending and rocking, so it may be related to this intertetrahedral angle, but it's not shouldn't be taken as an absolute guarantee, and that this relationship of the QN units is transferable between the glasses and crystals. But always there's this question mark overlying things because we don't have the theory. So you should test this by using another independent probe, such as infrared or X-ray photoelectron spectroscopy. So I want to come back to the network for a moment. And we mentioned there was network formers, network modifiers. And as we add modifiers, we change the conductivity and how many bridging oxygens in the QN species there are. I want to take a moment to look at the structural models that are out there and provide a bit of a framework for going forward in a more consistent, more rigorous way, perhaps, that's been pursued in the past. So one of the ways you can quantify is looking at the spectra and counting the number of each of the QN species by some method, I'll talk about in a moment. But you can also calculate from the QN species a mean number of non-bridging oxygens per tetrahedral species or per silicon. If you have an independent probe of the bridging or non-bridging oxygen, you can calculate what the ideal connectivity would be versus what the connectivity, the mean connectivity is from the MBO over T, and these should add up. They should be related together. The total bridging oxygen, non-bridging oxygen should be related to how many bridging and non-bridging oxygen there are on the tetrahedra in your material. So we're going to take these ideas and play some games with them to try to test structural models that we can use for actually gaining insight for prediction of how the properties might change as the network changes. If you've looked at this literature at all, you're probably familiar with two different equations. On the left is the depolymerization or polymerization reaction. Bridging oxygen breaking up into non-bridging oxygen is depolymerization heading to this direction, and polymerization is when you head to this direction. In addition to non-bridging oxygen, there's a third oxygen species that I've introduced here, and this is called free oxygen or non-network oxygen. It's not a radical oxygen that some people make the confusion with, but it just means that it's oxygen that's only bound to our modifier cations here. The much more common reaction you'll see is the disproportionation reaction. Q to 2 QNs goes to Qn minus 1 plus Qn plus 1. For example, if you have two Q3s, they can disproportionate into a Q4 plus a Q2, or if you have two Q2s, they go to a Q3 plus a Q1. It's important to note in these cases, if you look at the number of non-bridging oxygens, let's take the top equation here. There's our Q3, so there's 3 bridging oxygen, which means there's only 1 non-bridging oxygen, and it disproportionates into a Q4 with no non-bridging oxygen and 2 non-bridging oxygen on a Q2 species. So these disproportionation reaction cannot change the ratio of bridging to non-bridging oxygen, but it can change the distribution of QN species. Contrast this with depolymerization. So if you have pure silica and you add barium oxide to it, the oxygen, the free oxygen here from the barium, reacts with the bridging oxygen on the QN species to create 2 non-bridging oxygens, and you have this barium sitting in your network. So adding any metal oxide breaks up the connectivity of the silica tetrahedron. And we're going to look at how these two situations relate to one another. So let's define that a little bit more explicitly. So this depolymerization reaction here was first shown just based on stoichiometric considerations with no with no evidence to back it up back in 1954. And using the law of mass action, we can create an equilibria constant, K1, the products with where the coefficients are the superscripts, divided by the reactants on the left-hand side of the equation. And if we turn to how that looks on the graph here for a moment, we have 0% metal oxide added. In this example, Nesbitt et al. Used magnesium, calcium, etc. And you can have 100% metal oxide or 100% silica down here. We've seen that 100% silica has just Q4 species, and all the tetrahedra are connected to one another. So we have the 100% bridging oxygen, and along the y-axis is the amount of the mole fractions of the different oxygen species. As we add metal oxide, we break up the network, and as a consequence, the bridging oxygens decrease. Following this line here, focus on the dashed line for the moment. And as you break up the network and more non-bridging oxygens are formed, non-bridging oxygen increases, following again this dashed line. If K1 goes to infinity, so every time we add some amount of metal oxide, this reacts to form all the non-bridging oxygen it can, we say that K1 goes to infinity, and by the time you have 66% metal oxide and 33% silica, all the bridging oxygen are consumed so that there's none left in the system, which means that all tetrahedra have only non-bridging oxygen on them. This is Q0, and this corresponds to orthosilicate. All the crystalline phases have no bridging oxygens in them, in their structure, mineralogically speaking. And this should be also true in the glass. So many studies don't even discuss this. They just say that disproportionation goes to completion. So if we look at this mean connectivity, if we go to the mean connectivity we introduced in a moment and look at how these non-bridging oxygen are distributed across the tetrahedron, there's 3 situations set up. Situation 1, which is under this assumption that K1 goes to infinity, results in the MBO over T. Here, remember, there can be 4 oxygen per tetrahedron, so 0 non-bridging oxygen to 4 non-bridging oxygen. And here it increases non-linearly to the orthosilicate composition, 66%. where all the oxygen on the tetrahedron is non-bridging oxygen. If it goes to infinity, the mean conductivity should lie on this line. That means we've shifted the reaction all the way to the right-hand side, and we formed as much non-bridging oxygen as possible from the amount of barium we added. This is the case that was assumed in essentially all studies up until about 2010, sorry. And as a result, people have assumed this is true and fixed their data to this line. And this is where the inconsistency and the conflicting interpretations are entered into the scientific literature. But we have other situations as well. If K doesn't go to infinity, it's less than infinity, we can have the situation number 2, where as we've added metal oxide to the silica network, the QN, the MBO from the QN can be less than that predicted from the amount of oxide metal added. In this case, the glass is more polymerized than expected. So there are less MBO than expected, and you'll be sitting in this zone here on the bottom. This means that the reaction hasn't gone all the way to completion, and that we have excess bridging oxygen, which means that there must be some free oxygen in the melt. The final situation, if we count up the non-bridging oxygen, our QN, and we determine it from another method, we could have more non-bridging oxygen per tetrahedron than metal oxide added. In this case, we'd be in this field up here. This is termed the implausible, or some people would say the impossible zone. And the melt is ultimately less polymerized because there's more non-bridging oxygen than expected of the amount of metal oxide added. In this case, it's only possible in the rare situation where the coordination changes and that this tetrahedra, the amount of tetrahedron, amount of silicon, is not constant, and that means that the coordination number has changed. So in this case, this reaction is not the only thing that's happening, and you need to consider other alternatives. For most silicate glasses at ambient conditions, there has basically no compositions, with one or two very specific exceptions, that the coordination change of silica changes anything other than 4. So silica must be 4, and you can say that this is indeed impossible at ambient conditions, but that may not be true at higher pressures. So let's consider this a couple consequences of equilibria is less than infinity, and in this example, we'll choose a K1 value of 60. There are a couple consequences. First, bridging oxygen, remember it's at 100% here, will persist to higher compositions than expected. And even in fact, up until, in very small amounts, up until you have 100% metal oxide. Conversely, if there's more bridging oxygen, there is less non-bridging oxygen, and so the non-bridging to bridging oxygen ratio will change, and you'll have some situation here. As a third and final consequence of this, if there is some bridging oxygen, we know that there must also be some small amount of free oxygen. And the reason why this is controversial, or has been controversial in the past, it's not so much anymore, is that for this range of silica contents, I've lost the pointer. This range of silica contents, below 50% of modifier added, so at higher than 50% concentrations of silica, the concentration of this is essentially 0. You know, it's only 1 or 2, maybe 3%, depending on exactly how reactive you want to consider your system. So there's very few techniques that are sensitive to the 1 or 2% level of this feature. But this can lead to very inconsistent interpretations in terms of the proportion of MBO to BO in your melt. So in terms of developing a structural model, I would say this introduces a very large error into the proposed structural models at hand. And to prove that's not just my opinion, I've collected all the data for the barium system. And this is the same plot as before, but zoomed in a bit. Here's the ideal line. So K1 goes to infinity. All the free oxygen is reacted to form non-bridging oxygen. And you see there's sort of three trends in the data, and I studies on this line almost always assume a priori the situation one above. And so they force their models onto this land. In the case where the data hasn't been forced to fit this model, you start to see with an increase above activity, this a possible zone. And for this system, we are absolutely sure that there is very essentially no coordination change. And so these represent a situation where the structural models presented are actually invalid. The third set of data scattered is my own fit, not using any of the assumptions. And you see there's some error within about 5% of the line here. So you would expect some error if you're not imposing some assumptions on your model in the first case. So use this as a test for evaluating when you pick up an article whether the model is credible or not, and if they've actually made this test or not. But how do we quantify the spectra? I'm going to try, I see I'm running short on time here, so I'm going to go a little bit faster in this section so we actually get to the examples before our time is up. But to look at all these peaks we've been showing today, we need to describe them by some line shape. And any line shape has at least 4 parameters. The full width half max, which is the width of the peak, this width here. The position, the frequency, so in this case, the band is at 1076, is centered right here. Its absolute intensity or relative intensity, as we saw, and then we can integrate all those parameters to get the area under the curve. These are the formulas for how the intensity decays as you move away from the center. And just to say that if you have a pure crystal, you should be using Lorentzian line shapes because they accurately describe the photon-phonon interaction probability. The other alternative that's very commonly used in glass literature is that you use Gaussian line shapes. This would be expected if there is a random distribution of similar Lorentzian line shapes in the spectra. What's becoming more in vogue is the pseudo-Voigt line shape, and this is just a combination of both the Gaussian and Lorentzian line shapes. There's many, many other different line shapes that you can use, but I opt for simplicity because all of these other line shapes have more model fit parameters, and therefore you can mislead yourself into believing you have a better fit than you do. Some examples of this. This is the same spectrum fit in 4 different ways, again from Professor Almeida. On the top left here is a situation where 3 Gaussian bands are fit. And you can see they get the peak here, they hit the peak at the top, and they get the shoulder on the high frequency side. But you can see that there's some gaps here. The center of the peak is not very aligned. There's another gap here. And so we would consider this quite a bad fit, and certainly you should not consider making an interpretation on that. If you put 4, add another peak to fill these gaps, for instance, but leave it totally unconstrained, you'll get the fit here. And the sum of these peaks really well reproduces the spectral envelope, so the peaks and valleys here. But you'll see that there's high degrees of overlaps, and you have peaks with very similar centers, but with very different shapes. This is quite broad, this is quite skinny. All of these guys overlap in this region here. For me, this is too much overlap. We don't see this type of behavior in crystals, so I would consider this a very poor fit as well. Finally, on the bottom, you have Lorentzian line shapes and a pseudo-Voigt line shape. And just to show you the difference, here's the 4 peaks. Both of these fits reproduce the overall features in the spectra, but you'll see that when the pseudo-Voigt is on, you have quite broad line shapes, whereas when a Lorentzian is used, the peaks are quite narrow. There's still some overlap, which tells you that this overlap is real, not to be dismissed, but the centers don't overlap too strongly, which gives me a confidence. Since even though both are good fits, let's say, since in the pseudo-Voigt case you have an extra fit parameter, I would opt for the Lorentzian fit as the best fit because it has the fewest amount of parameters that you modify and best reproduces the spectra overall. In general, this would be an okay fit. But I mentioned that we want to have physically reasonable values for the center, for the width of the peaks. And we know from melting crystals and following them that the QN bands are produced in both of these. And I will skip ahead here for timing's sake. But this is a study on metasilicate crystals, which have just two Q species. On the left-hand side is a plot of the center, the frequency, as it's displaced from its frequency at ambient conditions. And here's the full width half maximum. So the width of the peak, again, normalized to its width at room temperature. These trends are displayed here, are described here, sorry. But in both cases, you see that both the shift in the center as a function of temperature and the full width half max shifts consistently, despite having different symmetries and different chemistries. Again, calcium, lithium, a mixture, magnesium, calcium, sodium, they're all following the same trend. So this gives me confidence that there's a systematic behavior in these stretching modes for crystals. And let's see how that compares to some glasses. The shift is a little bit different because the center is different for the glass systems. But if we look here, on the left-hand side is the same plot for the full width half max of the glass species. On the bottom is the crystals. On the top is glasses. If we heat up a crystal to its melting point, the full width half max happens to coincide with the full width half max of glass. And if we heat up the glasses, the trend here is exactly parallel, despite having completely different compositions. Again, sodium, lithium, calcium. For the glasses on top, there's cesium or potassium. This tells us that the broadening due to temperature can be accounted for just by having your width be constrained in the glass by that of the band in the crystal at its melting point, which is for Q0 species around 40 wave numbers, and it increases from there. To show that this is even more broadly applicable, and not just a simple fact that we've chosen some nice systems here, this normalized shift in terms of the peak center relative to that at ambient conditions. Here we have this normalized plot, including silicates such as magnesium orthosilicate and lithium disilicate, but also a lithium orthophosphate and lithium orthosulfate. So it turns out, although there's a bit more spread in this data, there is a very consistent peak shift with temperature, and similar trends are found with the full width half max of these phases, although in the case of the full width half max, they follow slightly different trends here. But all this is pointing to the fact that these stretching vibrations, whether it's silicon oxygen, phosphate oxygen, sulfate oxygen, have similar physical parameters that tie the crystals and the glasses together. And hopefully more people will use these parameters so that we can make our fits not just reproducing the envelope that we saw earlier, but have the physical parameters expected of the same vibration going from the crystal into the glass. And ultimately, at the end of the day, if you see fits with full width half max very, very large, we see this full width half max larger than 60 would be up here, a glass at a very high temperature, 1400 degrees Kelvin. And so fits with full width half maxes very large are probably unrealistic, or the vibration is not the same stretching vibrations that we see in these crystal phases. I'm going to speed through here. Just some final thoughts on curve fitting. Your overall peaks should follow the envelope, and we saw a bad fit is where the peaks don't follow the envelope. Try to use the minimum peaks as necessary. And if you can, use some suite of samples that's changing the same peaks with pressure, temperature, time, or composition, or some other reaction, so that you can follow the peaks. And even if you don't get an absolute model, you can still characterize the relative behavior of the peaks based on your other variables. I would highly recommend in the case of silicates to look through the work of Nesbitt because we're starting to realize that these stretching modes in particular related to the Q-bend bands have very small ranges. They can't just be anything. You can't have a band of 100 with a width of 100 wave numbers and call it something that we see in crystals. At the end of the day, because there's no theory, we should all be a bit humble. You never know when you have a peak in your spectra, what's under there. You could have elephants or snakes. So I recommend a degree of humility, and so long as the data treatment is consistent, that their model is at least to a small degree possible. I realize we're running out of time, so I'll just go through quickly some samples of applications. Here is an application to crystals. In this case, the aluminosilicates albite and anorthite. In the plot here, we see our Raman spectra with the various peaks. We have 0% or 1% anorthite here, all the way to basically 100% anorthite at the top. And these guys, Bersani et al., they have created a standard based on this parameter delta CB. This delta is a function of the peak positions here, which I haven't put on the plot. But the peak positions ultimately in their shifts shift linearly as a function of composition. And so here on the rightmost graph of your screen, the composition determined by Raman is on the y-axis, and that determined by microprobe analysis is on the x-axis. You have a very strong linear correlation between these two, suggesting that a Raman spectra that, again, you could take all of these in maybe 10 minutes without much sample preparation, can leave you with a very accurate determination of the composition. Of course, if you're worried about minor impurities, you'll still need to do the microprobe, but this shows the amazing power of composition, the amazing power of Raman on the composition of crystalline phases. If you're interested in super strong ceramics, such as enstatite-based ceramics, Tribadino et al. A few years back created a similar, took Raman spectra going from the diopside composition to the enstatite composition, and they showed that as you substitute magnesium for the calcium in the modifier site, at some point there's not enough, the magnesium's too small and the chains kink. And so as a result, you reduce the symmetry, and this enstatite rich phases have a P2-1 over C symmetry, whereas the diopside phases have a C2 over C symmetry. And during this reduction in symmetry, you can see here happens around 50% of diopside, you have a splitting. This is quite obvious in the spectra. And when you see this bland splitting, you have this phase change with different symmetry that we've discussed. So if any of you are studying phase changes and you know what the Raman spectra is of the two different symmetry phases, Raman is extremely sensitive to these situations. I will skip this for the sake of simplicity. Another example of a sodium silicate with a little bit of aluminum and phosphorus added, they noted that there were gigantic structural changes, quite strong structural changes, as the amount of phosphorus was added from 2 to 4 to 6%. The bands here grow quite intensely, and the second and third bands grow intensely here. These are related to the formation of orthophosphate and pyrophosphate groups in the melt. Because these have one bridging oxygen and no bridging oxygen, there's this evidence to show that there's quite a strong phase separation between the phosphate and silicate networks. They also looked at quench rate. So here's one composition with 6% phosphate. As they slowly cooled it from 1,000 degrees with time, they noted that the pyrophosphate groups decompose into orthophosphate groups. And so you have this depolymerization happening within this system. They also looked at phase separation in the system. Without going into the gritty details, You can track the bands, their position and intensities during phase separation or during crystallization, and you can see how they evolve with time here in the system and relate these behaviors with the Avrami equation to look at the dimensionality of these processes. Another great example of broad interest is ion substitution glass. For example, that which it produces the supersonic screens on your phones. When in this very complicated, but ultimately another sodium silicate glass with a bit of boron, aluminum, zircon, and antimony mixed in, when they left it in the the silver nitrate bath, they showed that as you go into the sample, this peak at 1070 decreases and the peak at 1080 increases. So they show that not only are there tensile stresses building up in the surface of the glass, but you're actually changing the structure. And as the silver content increases towards the surface here on the left hand of this graph, you have less Q3 and more Q2 forming. This is guaranteed to change the properties present in the glass and it's ultimately its strength. So just a warning, if you think you can apply the Raman spectra of anything, it gets quite complicated quite quickly, and there's lots of band overlaps, especially if you're interested in borates. And I'll stop on this slide, but there's a lot of similarities between silicates and phosphates. For instance, instead of being 4+, phosphate is 5+, and as a result of the need for an extra electron here, there is a double bond of the phosphorus to one of the oxygen. And this prevents an extra linking, which means the only difference between phosphates and silicates is that you can't form Q4 species. You only form Q0 to Q3 structures. This is what the Raman spectra on the left-hand side show. At the top is pure phosphate glass with 0% lithium. As we increase the lithium content all the way to the super phosphate here with more lithium than the orthosilicate composition, we see a smooth shift to lower frequencies related to the QN phosphate species, with the only difference that there's an extra band here at the highest frequencies related to this double bond. It's quite strongly bound, so that shifts it to higher frequencies. And otherwise, you have the Q3 band somewhere under here, a Q2 band comes in, Q1 and Q0 forming. With that, I will skip ahead to the end, but I want to thank you for your attention. Thank you for your questions. And if you are interested in discussing, please stick around. I'm here to stay for a bit while I discuss any other questions you might have. But before we do that, I'd just like to thank my PhD supervisor, Grant Henderson, and a colleague I work with, Boris Monk, who is now at Elford, Daniel Neuville, and John Dubesse, guys from France. They have inspired me to do this work, and they have also allowed me to use their slides for this talk. So with that, I thank the Iranian Ceramic Society. I thank ICerS for hosting and for the Glaciage for hosting me. And I hope I've brought up some interesting points and stimulated some new ideas that will motivate you to make better research and ultimately better glasses and glass ceramics. And with that, I will turn it over to ICerS for any questions you might have. Thanks again.
Oh, thank you very much, Ben. It was a very nice presentation, perfect, it was awesome. So thank you very much. Maybe we have some question we can ask you, or we can switch to the discussion panel, then you can also see the questions and read them if you agree with me. And you can turn on your video if you want, but I think still you have some problems with your webcam, I think. Let's try it again. Yeah, I lost the question. Oh, now you are freezed. Just play a little bit with your webcam to see if it works. No, let me just read the question.
So,
Can
I
you
see
read the
there's
question yourself? We have a question from Zohra Hamnabar.
yes. So, yes, as a first order model. So, okay, sorry. The question is, we determine the field strength in glasses. Can it be said that glasses with high field strength, their Raman peaks shift to lower wavelengths? As a general comment, yes, the field strength is related to how strongly bonded the two elements are. Uh, and so, if you have a stronger and more covalent bonds, you have a shift to higher frequencies. And if you have more ionic or weaker bonds, you can go to the bands will shift to lower frequency. The only caveat or caution I would recommend is that you have two effects. It's not just the bonding, which the bond strength certainly affects the vibrational frequency, but you also have the ability to polarize that bond as well. So you have to be a little bit careful of these two effects. But otherwise, in general, absolutely you can say what you're saying. So I think there was a question about summarizing my presentation.
Yeah,
If I could summarize it in just a few sentences, I would say the following. Raman is extremely powerful, and you can use it for almost any material you want. It is fantastic for silicates because of the wide community of users that have built some great databases. And so even if you're not so familiar with knowing what vibrational modes correspond to what crystal, you have easy access to that information so long as you can find it in the database. For all the major mineral groups, this is already well known for the silicates. I can tell you that 100% certainty. So if you work with silicates, no problem. When it comes to glasses, it's much more complicated and there's no absolute right answer, but I would highly recommend you looking at the similarities between either a suite of glasses or between crystals and glasses of the same composition to get an idea of what's going on. And if you want to come up with a rigorous structural model, one that will allow you to predict the properties and modify them to your will, you will need to take your time and really think about it and use probably Raman plus another technique. So Raman is really powerful for all different materials. For silicates, it's excellent. The databases are well developed. For glasses, it's much more complicated, and it really takes some time and some experience to do a good job of that. So hopefully that makes sense, and that was a reasonable summary. There's a question here, I think, in Persian, Maziar. Perhaps you can
it is
read the one from Side.
we call it English, English Persian for English. Yeah, you don't need to read that question. We will have a question from Naji. Please go to question by him. Yeah, is there a way to deconvolute?
Right. So two things. So there's a lot of misuse of nomenclature, not just with the structural aspects I've talked about, but deconvolution is one of them. Deconvolution is a specific mathematical operation, which I forget off the top of my head. And what you do in Raman spectroscopy is curve fitting. So that's just a small modification to the language there. We do curve fitting because we don't have this absolute theory to describe the vibrational modes. But that being said, is there a way to separate the PO stretching modes from the silicon stretching modes? So let's go back to our presentation here. Right here should be the phosphate. If you think back to the silica vibrational modes, they highly overlap here. And if you are careful, you can see, you can probably separate, for example, if you did a series of compositions, including more or less phosphate or silica, where the frequencies should be. And I'm not going to say there's an absolute way, but there definitely, it's possible to model the spectra, put some curves based on your phosphate end members and your silica end members, and come up with a model that will separate the SIO and the PO vibrations. Then your follow-up part of that question. So it's possible, but it might not be easy depending on how much overlap there is. The same goes for borite, boroxyl rings, trigonal boron in threefold coordination versus tetragonal boron. To my knowledge, and I have not worked on borates, but to my knowledge, you can see in this graphic here where you would expect vibrational modes from B3, trigonal boron, and B4. And you can see that the B3 vibrations are typically at lower frequencies than the B4 vibrations here in the middle or here. That being said, it depends on a couple things. First, B3 trigonal boron is usually only found at low borate contents. So if I remember correctly, the limit's around 30% or 25%, somewhere around there. And at higher concentrations of modifier, you only get tetragonal boron. But that being said, it really, I would have to see what compositional suite you're talking about. It is certainly possible in some, for some compositions to differentiate between PO3 to PO4. But if you have a really complicated composition, I know sometimes the vibrational modes can merge together and just look like one big broad hump, and in which case you cannot. So hopefully that answers Naji's question. Thank you, Manuel.
Yeah, then we have question. Yeah, we have two more good questions. One is from Abul Qasim. He's asking about the low percentage of the, I don't know, most of the example are some of solid solution. What about low concentration secondary phases? Precipitates, less than 3 mole%.
That's a great question.
Probably he wants to discuss also with you. His microphone is on. If you want to speak, please speak and ask your question in details. Abul Qasim.
Yeah, go ahead.
No. He's just raising his hand. Okay, go on.
No worries.
Hello.
Hello.
Hello, Abul Qasim.
Go ahead, please.
Hello. Thank you very much for your nice presentation. I have a few questions. First, the first is that I already wrote. As I noticed, most of the examples that you presented consist some solid solutions. But for example, in the case when you have, for example, you have added some, for example, sodium oxide. So, for example, it's possible that you have some precipitates. How you can distinguish the precipitate from solid solution?
So thank you for your question. There's a couple different aspects to the answer. First is the spatial resolution of Raman is quite high, as I mentioned, microns level. So if those precipitates have a size that is, greater than a couple microns, and you can get the Raman beam on them, even if it's about a micron, so long as it's not too much less than half a micron, actually, you can get a good Raman signal if you're willing to take a long enough spectrum. So if, for example, you have a colorless glass and you have a colored phase, it's quite easy to identify those minor secondary phases. And if you can get the Raman on it, you can get a spectra and identify it. If, on the other hand, you have a ceramic that is not so translucent and you don't have any phase contrast, you can't identify the phase optically, for instance, the next best way is to look at doing a Raman map. And so you will look at the intensity of a peak or a series of peaks, and you raster over point by point over the sample. And you can do one of these days. They're really, the Raman companies are developing this technology quite heavily because it's used in pharmaceutical testing. You know, when you're producing a lot of drugs and tablets, you want to make sure you have the same phase, and you want to make sure that you don't get these precipitates and secondary phases. So they take a Raman scan very quickly over the surface of the sample to make sure that they get the Raman response of the phase that they're interested in, and that they don't have these anomalous peaks entering into their product, because that dictates the quality and consistency of what they're putting in. So if you're willing to wait the time and do the mapping, you can identify, you may be able to identify these phases. But if it's at low percentages, you know, if you don't hit those minor phases, then you're just not going to see them. So it takes time is the bottom answer to it. Hopefully that answers your question.
Okay, can I continue? Can I continue?
Yes, go on.
Our samples consist of both bulk ceramics and also thin films. In the case of thin films, we have many experience with SACs, you know, small angle X-ray scattering, but not useful. We have not been able to distinguish if we have a solid solution or we have a precipitate. We could not distinguish because small signals and a lot of, you know, huge background. Do you suggest? Our samples are barium titanate. Our samples are barium titanate, and we dope some different dopants, and it's important for us that these dopants locate in A site or B site. You know,
Yes.
Essentially very extremely affects the ferroelectric properties of the material. And we have no idea. We have no idea if we have a side, B side, or a secondary phase. You know, did you understand?
Sure. Yeah.
Okay.
So as I said, for classical Raman scattering, everything I have described today, the limit of resolution is about a micron. If you are talking SACs, you're probably talking nanophases.
Yes, of course.
And you're just not going to hit that with a Raman, with a classical Raman. That being said, there are other techniques like tip-enhanced Raman and Raman coupled with atomic force microscopy. They can get down to those scales. I don't know exactly a lot about those techniques because I haven't used them in detail. I've just read a little bit. But you have to look at one of the more advanced Raman techniques. So tip-enhanced Raman or surface-enhanced Raman or something. Unless you know where these nanophases are, I suspect that is going to take you quite a bit of time. But
Sure.
It might be worth it.
Yeah, and I don't know, Abul Qasim, if we have these techniques in Iran. I don't know. We should search for it. I think the new Ramans in the Iran. No, I don't know.
So.
You don't think so?
Yes.
Oh, okay.
We have some Raman, you know, instruments. For example, in Kashan, I think for example, in Polymer Institute of Polymer. You know the Institute of Polymer?
Yes,
of
yes.
Iran.
Yes,
Institute
yes.
of Polymer. Okay. But I think, as Professor said, probably there are classical Raman sample instruments. Yeah. I think.
Okay. Thank you very much for your question.
Yes, I would just add to that in the end. A lot of the new Raman setups are being sold with the AFM and the tiers techniques attached. So you never know. You have to see who bought it and ask them if they have these techniques possible. But thanks for good questions.
Professor, excuse me. For example, in the case of this problem, maybe we should go to thick films. Yes, probably. you suggest that we go to thick films and test it in thick films.
I mean,
To be honest, thin films are not my expertise, so I would say see if they've done it in the literature.
Sure.
yeah, thank you very much, Abu Hassan. Thank
Yes, thank
you.
you.
Yeah, we missed one more question, Benjamin. It was in Persian. I will translate it to he wants to know about the ability of Raman to do the test on organic material like oil or other stuff. But I think you can just comment on it briefly.
Sure. Um, I'm not a guy for organic materials, but I do know that absolutely 100% ramen has been applied to the oil industry, and the different chain lengths of the hydrocarbon, as they have bigger chains, the effective mass of those larger particles will be greater, and you will shift the Raman vibrations to lower frequency as you increase that mass. So I don't know specific examples, but for sure it's being done. It has been done, and it's continuing to be developed. Raman on hydrocarbons. I showed one slide earlier on where the carbon hydrogen vibrations are typically at high frequencies, I think around 3,000 or so wave numbers. That's because there's quite a strong covalent bond in the hydrocarbon. So it's for sure there's sensitivity to organic molecules. If you're really interested in organic molecules, you'll probably want to look at red wavelengths because sometimes you get strong absorption and you tend to burn things if you have a lot of power on the sample. So just be careful with that when it comes to organic samples. Thank you for the question. There's a question here about the best method for what's the best method for convolution of the spectra. So there is no simple method, and that's what I alluded to in the discussion here. What I would say is if you have, what I would always recommend is starting with a compositional suite or a crystal of the same type. So, for example, let me just go back a bit for a second here. We showed some examples of deconvolution. It turns out that for the stretching modes of a large number of materials, in this case, we have examples of phosphates, sulfates, silicates with various counter ions here. All of them show a similar temperature dependence. And if I'm not mistaken, if I remember correctly, the, the, the phosphates, sulfates, and silicates have very similar trends in their full width half masses. So if you're trying to make a curve fit from scratch, and you don't if you want to do something that has some physical basis, look for a crystal and see how the center shifts, how the width of the bands shift as that crystal is heated or cooled. And use those parameters as starting parameters for your fit as the glass, and then add extra bands as you need them. And I will leave, as I mentioned, I will get Mosiar to post this presentation afterwards. And when I do so, I will include all the references in full that I borrowed their figures. So you can go back through here, and if you're interested in silicates, phosphates, sulfates specifically, or some of these other more complex glasses, you will be able to look through the literature of them. And as I mentioned, I'll include my email address, so feel free to shoot me an email. I've read widely about these subjects and thought a lot about them, as hopefully you've seen. And so I would happily share any good examples I can pass on. But to answer your question, the best method, there is no best method. But for me, it starts with using physically reasonable parameters and not just letting the program shift the peaks around and broaden them out to all sorts of conditions. So that's that. Thank you for that question.
Yeah. Another question is about machine learning, I think. Is there any
Is there
work?
any work to combine machine learning with Raman data groups for glass characterization? Naji, this is a wonderful question. I really appreciate that you brought it up. And I wanted to put something in my presentation, but I already had so much already. if we go back to the beginning here, and we look at this map here, should be right here. So in this case, you're getting a spectra from every pixel on your sample. This is oodles and oodles of data. This is the future, is this imaging techniques. There is no way that you can individually process all these spectra to extract the information, which means you need to write some algorithm to do so. And a lot of people are trying various types of machine learning and advanced statistics to process this data automatically to extract the information that one needs, and perhaps new information that might not be available if one is thinking about with our simple brains. So there is a ton of examples of machine learning applied to Raman, and I cannot state enough that the examples are best described in that book by Max Diem on Raman spectroscopy. I have it here. I'll include it in the references in the when I post the slides, but it's the next one. It is somewhere shortly hereafter. No, a little bit further on. But Max Diem, modern spectroscopy, modern spectroscopy and microspectroscopy. This reference here. In this book, he talks about machine learning and all the different types of algorithms to extract data that are being developed. This is going to be the future of Raman. As we collect more data, we can't process it by hand. But with that being said, I highly recommend, if you're working with glasses, to avoid this at all costs because there's a lot of covariance in the peaks. There's a lot of peak overlap. And so machine learning, if we don't know those physically realistic values, the machine learning is not going to be able to tell us because of the covariance and all the peak parameters that are produced in these broad spectral features in glass. So with that caveat, machine learning is the future. Max Diem gives a pretty good introduction.
Very good question. Naji is still typing. And I think he has worked a lot on the Raman. I think I can see his CV now on the screen. He's Google Scholar, so he has some publication on Raman. So he's writing. Yeah. Another guy is writing.
I don't know what I'm doing.
Yeah, Ben, you closed our chat room.
Sorry, I accidentally. No, do you know how to get back? Sorry, Mazir.
No, I will change the discussion panel.
Thanks.
And yeah, then I will come back here. I don't know. Yeah, no, I think it's okay now. Let's wait a little bit.
Is it back?
No. I don't know. Pod. Let's see. Chat. Yeah, I see the chat room, but we lost our previous questions. Or I think so.
Sorry, please type your question again.
Yeah, we don't.
Sorry
don't
about
have
that.
more questions. No, I don't see any more questions.
There we go. Oh, somebody's typing.
Yes, thank you.
Hello, how are you doing?
In continuation of the last question, I wanted to know how, what's your idea about the resolution of the technique? For example, in the case of ceramics, ceramics is the knowledge of additives, and additives have a great contribution in their properties. You mean sometimes even trace impurities affects greatly. Did you notice what I mean?
Yeah, I think Benjamin has already
I mean,
answered your question, I
what
think.
about
Huh,
the
Ben?
resolution? I mean, for
Well,
example, the example that he presented was started from 3 more percent. Do you think lower amounts? What about lower amounts? For example, trace
that's
amounts. Do you have any experience
sure.
distinguishing the trace amounts of this, for example, impurities or secondary? In this case, the impurities.
Um,
Yeah, trace amounts of the
okay, let's.
impurities.
This is a very broad question, so let me answer in a couple different ways. Let's. I didn't have time to present this example, but here is a borosilicate glass where they've added phosphate and neodymium in trace amounts to model the fission products of nuclear reactant, for example. And what they wanted to do was to get a crystal phase to precipitate and stabilize, and that would host the fission products, and neodymium in this case is their example, and remove it from the glass so that as the glass broke down and crystallized, the any of the fission products or neodymium will be trapped in the crystalline phase and not be released into the environment. So I don't know what the concentration is of neodymium in this sample. I forget off the top of my head, but you're talking, sub-percent level.
Sure,
And
yes.
when they did linear mixing, so they took these spectra here and they treated them at different temperatures for 2 hours and looked at the product, and you can see this gigantic peak rose out of the middle of the spectra. They did a linear combination of the spectra for apatite, uh, here in red. This is the apatite spectra with this strong peak. And then they made the initial glass here free of neodymium, sorry, here, and then the glass with neodymium. And they tried to make a mixing to reproduce the spectra of those treated samples I just showed. And what they showed is that you do form this crystalline apatite. Alpha refers to apatite. And you do have a reduction in the amount of glass, but you don't have a reduction in the glass without neodymium. So their result was not successful, that in removing the neodymium from the glass into the apatite phase. So where that applies to your question is that even though they didn't have a signature from the glass, or a signature, let's say, specifically associated with this sub mole percent neodymium, they do see a large change in the spectra of the glass itself. And so what the limit of that resolution is, I don't honestly know. But depending on the elements, particularly if you're talking about rare earth elements, there's some pretty strong changes in the spectral features that you can see. For example, in our lab, we've done dopants of rare earth elements down to 0.1%. And you can see a peak coming from those dopants at 1%. But there's no generic law I can tell you for that. It depends on the dopant. You know,
Sure, yes.
rare
I
earths
understand.
tend
You mean
to
the
have a
feature,
strong
the change,
signature.
the change in the feature, you mean? That probably.
Yes, yeah,
Yeah,
exactly.
okay. Yes.
And so also to think about is the change, not just of the thing you're adding, but the effect on the spectra of the original glass, for example.
Sure, of course.
Uh, so, so you have two things. And what the ultimate sensitivity of that is, good question. Um, but there's other things, for example, titanium. If you add titanium to the glass, the polarizability of titanium is huge. So even with like 4 or 5% titanium or less, down to 0.5%, you get quite a strong band of it. I'm just trying to see in my extra examples here. Um, Here's the example of titanium, a spectra with titanium. This only has, in this case, it's 7% titanium. And so even with just 7%, you're getting a huge peak here. That's almost as intense as the silica bands, but from 10% titanium or less. And so you can track this down to quite low concentrations. Yeah. So hopefully that gives you some idea. But it really depends on what you're talking about.
Yes, thank you. Most of the materials, for example, titanium, zirconium, and the same have probably the same feature. For example, most of them are polarizable materials. The materials, ferroelectric materials, most of them, for example, titanium oxide, zirconium oxide, so on. Probably most of them are, show the same features, probably.
Yeah, for sure. So titanium, and I'm not so familiar with zirconium, but titanium shows those same stretching bands that are really intense, just like silicon. Zirconium as well. And if you're looking for minerals to get a sense of where the bands would be for zircon, for instance, or what's the zirconium oxide phase, these are published in the database I mentioned. So for sure, you can find studies where they've looked at the vibrational frequencies of ZrO2, TiO2, and where they occur when, for example, the titanium is in 4-fold coordination, 5-fold, and 6-fold coordination. There are plenty of studies. You mentioned before barium titanite. For sure, that's been studied, and we know where some of those vibrations are and what they're related to.
Okay, I will contact you later, probably.
Certainly.
Thank you very much
For
your nice presentation. Thank you.
Thanks for the good discussion.
Thank you, Abul Hassan. So we don't have any more questions, I think, and people left the room. We have 28 participants now. They're online, so we will wait a little bit more. We don't bother you more, Benjamin. You're hungry. I know it's afternoon and you need to have lunch. Then
yes,
just we will wait for one more question if there is any question. Otherwise, we have to say goodbye to the audiences. And let's see.
You are all most welcome. Thank you very much for coming out today. I really appreciate your time.
Thank you, Ben. I think there is no more question, I think. So as you said, as you promised to us, you will share your files as a PDF file. Then we can upload it somewhere. We don't know where now. So we will upload your file, probably the video, and people can access to your files and your videos. Then later we can also probably contact you to have more discussion or probably a collaboration.
Yes, check out the Glassy Age, and I assume the Iranian Ceramic Society website for some contact details and when the slides are posted. Really, thanks again. Happy New Year to everybody, and hopefully we'll do this again soon in the new year.
Yeah, sure. Thank you very much. Happy New Year to you, and I wish you all the best. I'll just pause the recording, stop the recording, then we can save it later. Thank you very much, Ben. Ciao,
Thanks,
ciao.
Talk to you soon. Take care, everybody.
Yeah, have a nice day. Thank you. Thank you. Bye bye,
everybody. Have a nice New Year. Stay safe.
Sure. Thank you.
آقای دکتر فایلا رو سلام مجدد. آقای دکتر منتظریان بله. آقای دکتر منتظریان فایلا رو گفتین کجا میذارید؟
ما توی وبسایت خودمون و یا انجمن سرامیک ایران. و حالا اگه دیدیم ویدیو خیلی خوبه و قابل آپلود تو یوتیوب هم هست که اونجا آپلود میکنیم، ولی من نمیدونم باید ویدیو ضبط بشه و چون اینجا الان ریکورد شده باید سیو بشه، بعد کیفیت سیو شده شو و حجمش رو ببینیم و بعد تصمیم میگیریم کجا در واقع شیر کنیم. هم ویدیو رو شیر میکنیم، هم پی دی افش رو احتمالاً تو همین سایت خودمون و یا انجمن سرامیک ایران میذاریم.